Hi everyone and welcome back to PrepFusion. So today we will start with the lecture 3A of our phasor diagram chapter. So today we will discuss about the parallel RLC circuits. So let's start with the parallel RLC circuits and how is the phase relationship. Is it lagging, leading, what kind of phase is there? So in parallel RLC circuits, what we will do is we will take help of the current. So if I is here, right, I is here and this is IR and IL, of course these are just magnitudes, okay, they have some phase associated with them. So I can write that my I will be phasor sum of IR plus I. Okay, now one important fact to note is the V is constant, right, across all of them. VR VL is same, right, because it is a parallel circuit, so VR and VL must be same. VR and VL must be same, that is equals to V input. So if I assume that my Vm sin omega t to be reference, then Vr also will have an angle of magnitude Vr angle 0. VL also will have an angle of magnitude VL angle 0. What about the currents then? What about the currents? We know current across a resistor is in the same phase as the voltage. So IR will be IR angle 0. But what about the voltage? What about the inductor current? Inductor current I know is lags the voltage by 90 degrees. Inductor current lags the voltage by 90 degrees. Why is it so? Because it is IL equals to VL divided by J omega XL, J omega L. So basically this J gives a lag of 90 degrees. So that is what we will do here. That is what we will do here is I will be equals to IR angle 0 and this will be minus J. This will have a phase of minus 90 because it lags minus J. So not mine, I will write here plus IL angle minus 90. Okay. So this is the case over here, right? Your magnitude of I, your magnitude of I is magnitude of IR whole square plus magnitude of IL whole square whole under root. What about the angle? So angle here, right? In which quadrant am I lying? So this I can write like this. This will be IR minus JIL. IL is just the magnitude, so it will be positive. So I am lying in the what? Fourth quadrant. So if I am lying in the fourth quadrant, then my angle of I will be minus tan inverse IL. IL is the magnitude, right? IL is the magnitude. So I just want to specify here because you will get confused. All these are magnitudes, okay? All these are magnitudes, else you will get confused. This is angle, this is with the phase angle basically. So magnitude of IL divided by magnitude of IL. This is the phase angle of current, correct? This is the angle of current. What is the angle of voltage? What is the angle of voltage? Resultant voltage. Angle of voltage, right, is magnitude of V angle 0 because voltage was reference in this case. So of course, again, what do I observe? I observe that my voltage here is reference in parallel circuit. Voltage here is reference in parallel circuit and my angle is just lagging. Angle is just simply lagging, right? Current is simply lagging. Current is here. Okay. Current is here. This is 5. Okay. So current will just lag. So this is my voltage and this is my current basically. So again, what kind of circuit is this? Lagging, because current lags the voltage, so it is behavior is lagging. So inductance is present, so the behavior will be lagging only. Doesn't matter if it is in parallel or series. Just I'm talking about just inductance. Okay, just I'm talking about just inductance. So we can analyze this using something else as well. We can analyze this using another method as well. So before that, I want to draw the complete phasor diagram. So V and I are here. So where is IR? IR, the resistor current will be in the same phase as the voltage, and your IL will lag the voltage by 90 degrees, because current lags the voltage by 90 degrees in an inductive circuit. Okay, so the combination of these two, IR and IL, will give me the resultant I. So is there any other way to solve this? Yes, there is. There is another way to solve this. Basically, what do I know? My I is equals to IR magnitude minus J IL magnitude. Correct. So I can write, what is I? I can write I equals to I magnitude of IR. Magnitude of IR is simply magnitude of V by R minus J. This is magnitude of IL, right? Magnitude of IL is what? Magnitude of V by XL. Okay, so I can take common the V. I can take out the V. V is a common term, that is equals to 1 by R minus 1 by XL. So this is what I taught in the previous lecture, that about admittance. So whenever there is parallel circuit, we we can solve easier with admittance. Okay, whenever there is series circuit, it is easier to solve with impedance. So this is what I by V is, what I by V is Y admittance angle theta Y. Okay, it is the admittance angle. Impedance angle is different, admittance angle is different, power factor angle is different. So three things are different. Okay, yes, all of their magnitudes are same. Why? Because here also, if you see, it is basically the division of current and voltage, right? If it is division of the current and voltage, that means angle will come what? Angle will be in subtraction. So it will be theta I minus theta V. Now, have we seen this before? Theta I minus theta V. Yes, it is the power factor angle phi. So the admittance angle and the power factor angle both are same. So admittance angle is equal to the, sorry, this is theta, that is the power factor angle, is equals to the theta Y, the admittance angle, is equals to the minus of theta Z, that is the impedance angle. So I should color this impedance angle. Okay, so I should color this properly. So this will be okay. So this is the these are the values basically. These are the values basically. So few things you should keep in mind. Okay, so again from here also you can find out the what admittance, equivalent admittance. So what will be equivalent admittance? Your magnitude of admittance will be 1 by R whole square plus 1 by XL whole square. Okay, what about the angle of admittance? The angle of admittance is basically, now again, right, in which quadrant is this? Fourth quadrant, because y is negative, x is positive, so it is again in the fourth quadrant. So angle will be same as the power factor angle or the current angle. It will be minus of tan inverse y upon x. Y is 1 by XL, x is 1 by R, so it will be 1 by XL upon x, so it will be 1 by XL, not x, sorry, 1 by XL upon R, 1 by R. So ultimately it comes out to be minus tan inverse R by XL. Okay, previously, right, if you remember, in case of series circuit, it was XL by R. What about the power factor angle? So power factor angle is the angle between theta I and theta V. Correct. Power factor is what? Power factor is cos of phi. What is cos of phi? Cos of phi, right? I have just told you cos of phi is same as the impedance angle. Just prove to you, right? Because it is theta I minus theta V. Because theta V is 0 in our case, because V is assumed to be reference. So V is 0. So it is simply cos of theta V. Sorry, theta Y, admittance angle. Correct? Or from here also, in the phasor diagram also you can see triangle you can do, right? Cos of theta, cos of phi. What will be the cos of phi? Cos of phi will be, this is the hypotenuse of the triangle. Okay, if my IR is here somewhere, okay, let me just reduce the size of IR. Let me just reduce the size of IR. So this is the triangle, right? So IR is in the base, so it is what? Cos of phi is what? Base upon height, sorry, base upon hypotenuse. Base is IR, height is, hypotenuse is I. So it will be I upon, sorry, IR upon I. It will be IR upon I. Now what is IR upon I? IR upon I is simply, IR is what? V by R. I is what? V by what? Z, V by Z. So it is now Z by R. So your power factor angle is different. Power factor angle is not the same anymore. Or you can ultimately write is that it has 1 by Ry. Ry is the admittance. So now I hope you understood, right, why I told you at during that point of time that don't mug up the formulas. If you mug up the formulas, then it will be very, very difficult for you. It will be very, very difficult for you. Okay. So other way around as well, if you want to, like, your power factor angle is just the impedance angle, right? So like if I draw the admittance triangle, so do I have space? That is the bigger question. So I will just draw here only. So this is 1 by R basically, 1 by R, and of course this 1 by JXL is lagging. So okay, let me just take it in the next page only. Here we have space, right? So if I draw it here, so it is 1 by XL. Okay, so this is my, basically the resultant is somewhere here. Resultant is somewhere here. Okay, so resultant is somewhere, this is my Y, right? Y. So what is the theta Y? Theta Y is this one, correct? The angle from the resistance. This is my theta Y basically, correct? So now if I want to calculate the cos of theta Y, because cos of theta Y is same as my theta Z only, sorry, my power factor angle only. So cos of theta Y, if I want to calculate from the, this is the admittance phasor diagram. And this is the phasor diagram of the circuit basically. So here cos of theta Y will be the base upon the hypotenuse. Hypotenuse is Y, base is 1 by R, so it is basically coming out to be Ry only. And what is Ry? What is magnitude of, like, this is the magnitude, right? So it is 1 by R into under root 1 by R square plus 1 by XL square. So like it is very, very difficult formula, no need to remember this, just understand how am I deriving it, how am I coming to the result. That is the more important portion. So remember, your Y can be written as a sum of G plus GB, where G is the conductance, or sometimes they write, what they do is they write it as minus B only, because they know, like, if I am taking the inverse of impedance, what happens is the angle changes its sign. So what is happening? So Z is some positive angle, right? It's a magnitude of Z plus 30. So what is admittance? Admittance will be 1 by Z, 1 by magnitude of Z. This sign remains unchanged. This plus 30 will go at the top, right? So it will become 1 by magnitude of Z minus 30. So sign interchanges. So what they do is, now it is nothing fixed. What they do, they write your admittance as Y equals to G minus JB. They can write it as plus JB as well. There is nothing fixed here. Okay. they sometimes, like, you might have this doubt why they write G minus JB. This is the reason, because the angle gets swapped while calculating the impedance, while calculating the admittance from the impedance. That is the only reason. There is no other reason. Okay, so from here you can write the conductance. What will be a conductance? Conductance, right? You will be 1 by R. Okay, and admittance will be, sorry, susceptance will be 1 by JB. So you might have a doubt, sir. So I will just write in the same next page that this is my conductance, and this is my susceptance, and this is my admittance. So what is the question? The question is, in the starting first lecture, if you remember, I told you that your conductance is not equals to 1 by R. If it is equals to 1 by R only for certain condition. But what was the circuit? Of course, your conductance value will change depending on the circuit. Now the circuit is different, so conductance will be here 1 by R. That circuit was different. Go back, turn over your pages, go back and see. That circuit was different. That is a series circuit from which I remember, and this circuit is different. This circuit is different, that circuit is different. Okay, or it was not a circuit, it was just a generalized expression. Impedance is Z equals to R plus Cx, what I remember, right? It was a generalized expression, but here it is a circuit. So according to circuit, the admittance susceptance will change. So don't just blindly memorize the conductance, the susceptance values. This will change according to the circuit. So here conductance is this, B is the susceptance, B is here 1 by XL. As there is already minus sign taken into effect of this minus sign, so we don't have to write explicitly here minus sign. If this minus sign was not here, if this was plus, then you would have written here minus. So just be careful regarding that thing. Okay, just be careful regarding that thing. So like these are the things basically. So I hope now you remember what is you can further simplify this if you want to further simplify, right? I don't just want you to memorize the formula, I just want you to know the method, how to find the power factor angle. That's it. That is the important portion, because like, this is not useful. This formula is not useful, right? Because you will anyways not remember it. So I can replace XL. XL will be what? XL is simply omega into L, right? Magnitude of XL. So it is omega into L. So it will be, if I multiply, if R goes inside, this will be 1. Okay, XL can go there. So it will be omega L divided by plus, if R goes inside, this will cancel out, this will be R square. Okay, so this will be the power factor angle formula, but no need to remember this, okay. Just how am I deriving the result, that much you need to know. So this is like the ultimate summary of whatever we have done. This is the phasor diagram where voltage and currents are given, how is voltage defined with respect to, how is current defined with respect to voltage, all these are given. Okay, and of course I have drawn the impedance diagram, phasor diagram as well. So this is the conductance here, okay, something is wrong. Okay, this is not this circuit is wrong. Parallel RLC circuit conductance is 1 by Z. No, this is wrong, right? This is for series. This result is for a series circuit. This is wrong. So let's ignore this fact. All these are wrong. These are wrong only. So here it will be 1 by so okay, let me remove this portion. So this will be basically 1 by R minus J 1 by XL. That's it. So from here your G will be 1 by R, which side I can further write this as G minus JB, which is equals to 1 by R minus J 1 by XL. So which is equals to, okay, no, I have already written it, right? So this will be, here my G will be equals to 1 by R and my XL will be equals to, so not XL, sorry, my B will be equals to 1 by XL. That's it. That's basically it. That will be the total summary. So now let's do the RC circuit. So RC circuit we will do bit on the quicker side. So here again the same analysis we will do. IR is equals to phasor sum of I equals to phasor sum of IR plus IC. So for a parallel circuit, so for a RC circuit, of course, you know, behavior will be leading. Okay, this much we know. So again, my voltages are all equal because it is a parallel circuit. So VR is equals to VC equals to V. Okay. What about the current? So current, right? I can write here I is equals to IR. IR is what? V by R. IC will be what? V by 1 by j omega c or xc, whichever one you prefer. 1 by j omega c. Of course, this time your current will lead the voltage. Current will lead the voltage, so this will provide a phase lead. So your I by V is basically equals to my admittance, that is equals to 1 by R plus j omega c. Okay, so your current leads the voltage. Your current leads the voltage. So your magnitude of admittance is basically 1 by R whole square plus omega c whole square. What is the angle? Angle theta y will basically be equals to tan inverse y upon x. Y is omega c by x. X is 1 by R, so it will be tan inverse omega RC. Okay. So it is that voltage now. So now if I like all the angles are found out, all this is fine. So if I, what else do I need to find? I need to discuss about the current phasor, right? What about the current phasor? So current phasor, we know that I is equals to IR plus IC, correct? And if I assume my V to be the reference, so if V is reference, so IR will be magnitude of I angle 0 only because it will be in phase, but IC will lead the voltage, so it will be plus J magnitude of IC. That is my I. So ultimately, if I draw the phasor diagram, this is my V, okay, V angle 0 reference, and from here I should have written this in the violet color. And now I will be IR angle 0. Okay, then the current will obviously be in phase with the voltage for the resistance, but for the capacitance it will be 90-degree leading with the voltage. So I will be lying somewhere around here. IC will be somewhere around here. So it will be something like this. So this will be the resultant basically I. So this is my angle from the reference basically, that is power factor angle, that is phi, that is equals to theta y as well. Okay, so from here as well you can derive basically what will be your power factor angle cos phi. Okay, this is the phasor diagram, basically I have drawn the phasor diagram. So from here as well you can see that the resultant current is leading the resultant voltage. Of course it will be a leading circuit. Of course it will be a leading circuit. So my cos phi is same as cos theta y is equals to the base upon height. Base is IR, height is I. So IR is what? IR is V by R. I is what? I is V by Z you can write, or admittance also you can write. This will be 1 by Ry actually, because this 1 by Z can be converted into admittance, so you get 1 by Ry. So few people will say, sir, I will remember this 1 by Ry formula for parallel, I remember 1 by R by Z for series. It's fine, you can remember, it's up to you. But in the question, right, trust me, in the gate question the circuit will not be this. It will not be this simple. Circuit will be something different. That will be not this simple. So for that case, right, this will not be the formula. This will not be the formula. Formula will be something else that you have to calculate in the exam hall itself. Okay, that's why I tell you, don't mug up the formula. Just mug up the analysis. How am I analysis the how am I doing the analysis of the circuit? So here this will be like, what is admittance? Admittance here, right? I have just already calculated magnitude of admittance, that is 1 by r omega c. So this will be r under root 1 by r square plus omega c whole square. So this will be 1 by under root 1 plus r omega c omega rc whole square. Okay, so this is my power factor angle, and of course your admittance angle also you can calculate using the same formula. Like here already have calculated, right? This also you can use, whichever one is suitable to you, you can use. Okay, so the analysis is same, nothing different. So admittance diagram I have not drawn, so admittance diagram I will draw the admittance angle. So what is my admittance? Admittance in this case is basically my 1 by r plus j omega c. Admittance is 1 by r plus j omega c. So this will be my 1 by r this will be omega c, and this will be basically 1 by r, like the admittance basically. So from here I can write, right, I can write the, this is my theta y. From here this is my admittance triangle, so leading, basically leading. So this is the leading triangle, leading admittance triangle, because it is a capacitive circuit. Admittance triangle. Okay, so magnitude of y is equals to omega c whole square. Okay, so yeah, very simple, straightforward. So that is what is written over here. Again, this is wrong, this is not correct actually. This thing is okay, we cannot select this. This is wrong anyways. This right is wrong because this was for the series circuit actually, that's why it is wrong. Okay, so it is 1 by z, which in this case is equals to 1 by r plus j omega c. In this case it is equals to g again minus jb. So this time your g will be 1 by r, but your b will be minus omega c. Just be careful regarding this, b will be minus because there is a minus sign already here. That's why I have to add an extra negative sign. So this was for analysis of the series parallel RL circuit, parallel RC circuit. This was the analysis for the parallel RL circuit. Now let's come to the RLC circuit, parallel RLC circuit. So what will happen to the parallel RLC circuit? So for the parallel RLC circuit, right, I have the resistor, inductor, capacitor. So again, similar to the case of the parallel series RLC circuit, we had 3 cases. Here also we will have 3 cases. Again, the current, right, will be phasor sum of all the 3 quantities. So if the voltage is reference, assumed to be reference, so my phasor diagram will be something like this. This is my voltage, and the current of the resistor will be in phase with the voltage. The current of the inductor will be 90-degree lagging with respect to the voltage, and the current across the capacitor will be 90-degree leading with respect to the voltage. I see. Now, like from here, you can simply solve this question. Like like, so not question, sorry, solve this equation basically. So your I, right, I will be what? I will be IR magnitude of angle 0 plus IL magnitude of minus 90 plus IC magnitude of plus 90. Okay, so of course you can see that this is minus j, this is plus j, so ultimately your I phasor comes out to be IR magnitude plus j IC magnitude minus IL magnitude. That's it. Okay, that's pretty much it. So that is the answer basically. So your I, now you can find out everything from here. If you want to find out the cos phi, all those things, so it depends what will be your cos phi, but your magnitude will be same, right? Magnitude will always be under root IR whole square IC whole square minus IR minus IL, not whole square, sorry, whole square will be outside, not here, so whole square will be outside, IR minus IL. Okay, so this will be the basically solution and answer. So this is the magnitude. What about the phase angle? So phase angle, right, will have three cases depending. If my IC, magnitude of IC is greater than IL, so of course it will be a leading circuit, so then the angle will be something positive. If magnitude of IL is greater than magnitude of IC, then the angle will be somewhat negative. But what about the impedance? Impedance also same thing only. If I just break this down into impedance, right, so your I is basically equals to IR plus IL plus IC. So this will be equals to I V by R plus V by JXL plus V by minus JXC. This we already know, right? Why is it minus, why is it plus, all those things we know. So what will happen? Your I by V will be 1 by R plus 1 by XC minus 1 by XL. J of course is at the outside. So from here again angle I will not be able to comment, but magnitude of course you will be able to comment. Magnitude of admittance, it will be one by XC. Okay, so basically what will be the admittance triangle? So admittance triangle will be somewhat like this, that my admittance like the conductance is here 1 by R, and depending which one is bigger, okay, is 1 by XC bigger, sorry, is 1 by, yeah, 1 by XC bigger, or XC is smaller, or 1 by XL is bigger. So this is 1 by XC, or I can write this as BC, okay, susceptance of the capacitor, or this can be written as 1 by XL, or the susceptance of the inductor. Whichever one is bigger, it will be that. If it is, if 1 by XL is bigger, it will be lagging circuit, otherwise it will be a leading circuit. If 1 by XC is bigger, it will be leading circuit, otherwise if both of them are same, if both of them are same, that means it is a unity power factor circuit. It will behave as a purely resistive circuit. So here first case is like from the currents as well, you can identify if my IC is greater than IL, that means it is a capacitive behavior. That means like the IC is greater than IL, that means resultant will lie somewhere around here. That means resultant current is leading the resultant voltage. That means it will have a capacitive behavior. That is what is written over here. If IC is greater than IL, basically it will have a capacitive behavior. So what will be the angle then? Angle will be basically my current angle, right? Theta I will be greater than theta V. Basically my power factor angle phi will be positive. My admittance angle phi Y will be positive. My impedance angle phi Z will be negative. Why? Because it is V over I. So I angle is more, so obviously it will be negative. Okay, so in the end I will summarize all the angles basically. So this, right, why is this the case? Because it is I by V. So if current angle is more, so I am subtracting theta I minus theta V. So if theta is more, so of course I will get a positive quantity. If I am doing this, this is voltage over current. So again here I am subtracting from theta V minus theta I. So again theta I is more, so I am subtracting some smaller number. I am subtracting bigger number from a smaller number. Of course I will get something negative. That's why I have written theta Z is negative. What is the angle? Angle, right? You can calculate tan inverse. It will be magnitude of IC, absolute value of IC minus absolute value of IL divided by R, okay. And will it be positive or negative? It will be positive basically. Why? This is my theta Y, this is my phi, because of course I am moving in the anti-clockwise direction. So this is the first case where it will behave as it will have a capacitive behavior, because my resultant current is leading the resultant voltage. What about here? Here what I see, resultant, whenever I am talking about current, right, it is I am talking about the input current basically, supply current. Okay, I am talking about the supply current. Here what is happening? Here if you see, your IL is more than IC. So what will happen is that if IL is more than IC, then I am lagging. So my resultant current is lying somewhere here. That means my resultant current is lagging the voltage. So it will be a lagging behavior. It will be a lagging behavior. Okay, so here what we can do is basically my magnitude of I will be equal to, like magnitude of I is same only. My I is basically IR plus J. This time IL will be higher, so it will be plus J IL. Sorry, this will be same only, plus J IC minus IL, magnitude of IL. But this time magnitude of IL is higher, so overall this will be something negative. Now if this is something negative, my angle will be minus of phi, because this is lying in the fourth quadrant. That's the only difference. Everything else is same only. So here basically my theta V will be greater than theta I. That means my power factor angle will be negative. That means it will be leading. My theta Y will also be negative. My theta Z will be positive. Why? Because it is V by I. Again, voltage angle is more, so that's why it will be positive. What about the angle? What will be the value of the angle? Phi will be this time minus sign will be outside, tan inverse mod of, this is mod of XC minus mod of XL. Okay, not XC, sorry, IC minus IL mod divided by IR. IR is positive only, or like I will derive in terms of the power factor angle, like the impedance angle as well. So what is your IC and IL? So your IC is what? IC is V by XC, right? Okay, I made a mistake. This should be IR, right? This is not R, sorry. This should be IR. So your here, right, I can further derive this thing. IC is V by XC. That is what? That is omega C. So I'm just talking about magnitude. So it will be omega C minus 1 by omega L divided by V by R. So like I'm not showing you the simplification. Okay, I'm just converting everything V by Z, V by XC, V by XL. I'm just cancelling out the terms. So ultimately this will be tan inverse of this. Okay, let me take the absolute value, otherwise you will have some confusions here. This is always positive, no matter what, this is always positive. Okay, so I'm getting a positive angle here as well. Same thing will happen. This you can write as minus tan inverse, same thing, omega. Okay, I don't have enough space here. Omega c minus 1 by omega l divided by r. Okay, so okay, so am I doing this correctly? Oh, okay, I made a mistake. This is like, that's why you don't do, miss the simplification. This is v by r, right? So if it is v by r will go at the top. R will go at the top. So here r will be here. That is what I was thinking. Somewhere I'm making a mistake. R will go at the top. So simplification, I hope you know, right? So this is what. So we'll simplify. So this is v by xc, and xc is what? xc xc is 1 by omega c. I'm talking about the magnitude only, and xl is what? Omega l. Okay, so what is your il is basically v by xl. This is xc, and what is your ir is v by r. Okay, so if you do the simplification, you will get back to this result. Here as well, this r will not be here, r will be at the top actually. Okay, minus tan inverse r omega c minus 1 by omega l. So the second like last case is the simpler one, where of course if il is equals to ic, of course my I will be equals to IR only, IR angle 0. So obviously my resultant current and resultant voltage will be in the same phase. Then my phi will be 0 degree, my theta y will also be 0 degree, my theta z will also be 0 degree, my power factor will be simply unity power factor 1 UPF. Okay, like it will behave as a purely resistive circuit, purely resistive circuit. Okay, so that is the case over here. This is the parallel circuit. Basically I have already discussed about the that magnitude. Now what is the frequency at which this happens? So this happens, of course, when my admittance is what? Only 1 by r. How can it be possible? My admittance magnitude is only 1 by r. How is it possible? My admittance magnitude was actually equals to 1 by r whole square plus omega c. If you remember, omega c plus 1 by omega. This is the condition for resonance basically. So this term has to be 0, right? This term has to be 0. Imaginary component, not plus minus. Imaginary component has to be 0. So this we will of course study in resonance only, that omega c minus 1 by omega l has to be 0. That means omega will be equals to 1 by under root LC. You ignore the negative solution because frequency has to be positive. So we write this as the resonant frequency, that we will learn in the next to next chapter. Okay, resonant frequency, this we will learn in the next chapter. So this is basically the behavior of a parallel circuit. I hope you have understood the basic thing, how to like my YRLC can be written as G equals to BL minus BC. Actually we write it like this. No, this right is, this should be BC and this should be BL. Like generally that's the method that we follow. This should be BC and this should be BL basically, because C is assumed to be positive in admittance. So from here if you want to derive, you can obviously derive the result. So this is already, like this I have already discussed, so I'm not discussing about this thing, the magnitude and all those things. This you can figure out. Okay, so yeah, just hold on. Yeah, so that's how we arrive to our expression. All the phasor diagrams I have drawn, all the impedance triangle. Impedance triangle I have not drawn. So impedance triangle, right, it's pretty simple, right? It will depend basically on the, this is the impedance triangle basically. It will depend which one is which. So here, right, impedance triangle will be something like this. 1 by r will be here, not impedance, sorry, admittance triangle. Admittance triangle 1 by r will be here, then 1 by xc and this. So the homework for you is draw, the homework for you is draw admittance triangle for each cases. Okay, that is homework for you. Now, right, like this is a summary basically. So summary, like it is written, I will not like explain much. Basically, right, your if it is a series RL circuit, that means what, your impedance angle is positive. So whenever it is a lagging circuit, your impedance angle will always be positive, your admittance angle will be negative, your power factor angle will be also negative, because voltage will lead the current and I measure with respect to current. So that's why power factor angle will be lagging power factor. Leading impedance angle will be negative, admittance angle will be positive, your power factor angle will also be positive, and current will lead the voltage. Same for parallel circuits, here I have explained. And for RL circuits, the impedance angle is positive, indicating lagging power factor. For RC, it is leading, so impedance angle will be negative. Admittance angle is always opposite to the impedance angle. So these are the few key points that you should keep in mind for parallel RC. For parallel RC circuits as well, the admittance angle was positive. Okay, no, admittance angle is negative, right? Or okay, sir, no, admittance angle will be positive only. If you see here, for parallel RC circuit, admittance angle was positive. Yeah, this one. For parallel RC circuit, the admittance angle was always positive. Admittance angle will be positive no matter what. For capacitive behavior, admittance angle will be positive. For inductive behavior, impedance angle will be negative. So same thing I have tried to explain to over here. Series RL, it will be leading, the impedance angle will be positive, admittance angle will be negative. Same thing. In the same table, I have just written the same thing, the different phase relationships. Okay. So like few considerations that I wanted to explain. So phasors are typically like defined between 0 to 180. So generally, this is a general trend. It can be, the angle can be more than 180 as well, but if let's say the angle is more than 180 or something like negative also we can choose. So I should have written it should be between 180 to minus 180 to 180. This is generally general thumb rule. Okay, it is not like certain that you have to follow this thumb rule only. If for a certain case you get the angle as 240, okay, what you do, it is nothing certain, but it's better that I reduce this angle to by subtracting 360, I reduce this angle to what, 120, minus 120. Okay, it is nothing certain, but just for our own convenience, because if I subtract 360 or add 360, it does not matter, because I come back in the same circle, right? It does not matter, come back to the same point. So that is one thing that I just wanted to mention here. So this right here, right, it is not between 0 to 180, it is between, the range is between 180 minus 180 to plus 180. So range will be between minus 180 to plus 180. This is the range basically. So here as well, the range will be between minus 180 to plus 180. Okay, so I hope you have understood this basic thing. So if I just do one thing, just increase the size of this, that would be actually okay, I cannot actually increase the size of this. Okay, yeah, now it is fine. This also, right, I need to increase the size of this. Yeah, now it is fine. So I hope you have understood like this basic thing. So what I want you to do, so in this lecture only we will solve all the questions. So I'm just showing you all the questions what we will solve in this lecture, and we will end our phasor diagram. So try it out by yourself, and after like, or what you can do, I can give you this as homework. I am giving you this as homework. Try all these questions by yourself, and in the next lecture we will solve all the questions. So yeah, that's it basically. This is the last question. You try to solve all the questions. That's it basically from my end. I hope you have enjoyed the lecture. If you did, make sure to like, comment on the video what portion you enjoyed, and yeah, I will see you in the next lecture. Until then, happy learning.